Good afternoon, everybody. My name is Mohammed Alula. Today, I'll be talking about our recent millimeter-wave research. This is work that is done in collaboration with my colleagues at Bell Labs, Zoran and Howard. Howard is over there. And also with Renee, who is at JKU Linz. So we start off with millimeter wave generally. Millimeter wave is expected to deliver major enhancements in indoor wireless networks. These enhancements are going to be brought about as a result of three main factors really. Firstly, we'll have a vastly increased spectrum in the millimeter wave band compared to the Wi-Fi 1. Which will translate into a substantial increase in data rate, in the communication sense, and in distance resolution, the sensing sense. Also, millimeter wave wavelength, the 60 gig band, is much finer compared to the sub-6 gigahertz band. That will afford us as well much increased Doppler sensitivity and consequently better ability to resolve motion for sensing. And lastly, the tiny wavelength will allow us to pack dense antenna arrays in small form factors, which will enhance our ability to do spatial multiplexing indoors as well substantially. So as a result of these combined effects, we believe there's an opportunity in reimagining how a future network indoors is going to look like. Primarily, we posit that if we think about adding a sensing primitive support at the lowest stack level, mainly at the physical level, then we're going to be able to do a host of new things. And those will make possible new compelling applications. One such compelling application is one that we study in this paper. We call it KinPhy, which is short for Kinetic Physical Layer. Kinetic stands for physical vibrations or actuation is one part of the equation. And those are readily supported nowadays in phone devices. All personal devices support such functionality in theory. On the other side, we've got routers that are going to have support for, they call them tri-band routers. These are going to support all the traditional bands so far, as well as the 60 gig band. So the combination of these two elements will form this KinPhy channel. Nonetheless, our ability to pull this off is going to be questionable, and that's exactly what we're going to look at in this paper, mainly because we're looking at really minute vibrational patterns that are of the order of micrometers really. In addition, phone form factors usually is quite restricted, and in turn the millimeter wave reflections that you get off these phones is not that big. So in a sense, this new channel is a form of a mechanical backscatter channel that we're going to look at in this paper. So I'll sort of dive into the technicality straight away, and then we'll revisit applicability to sort of applications towards the end of this talk. So to be a bit more specific now, KinPhy is comprised of three components. We've got a channel through which millimeter wave signals are going to propagate. This propagation is going to be a round trip one, so it's a back and forth. On one side of the channel, we'll have what we call meta surfaces, and that's what folks in the material science circles refer to reflective surfaces generally, in the general sense. These metasurfaces are going to actuate information-bearing vibrations, basically. And we're interested in reading these vibrations remotely. That reading is going to happen over from a device such as a router, as shown here in the picture. So let's begin with looking at the channel. There are a variety of factors that influence the attenuation that these millimeter wave signals are going to experience through this round trip. Probably chiefly among these factors is distance. There are also other things such as alignment of surfaces. Distance in this system is going to result in a signal strength decay that is proportional to the fourth power of the distance traveled. So, as such, whatever metasurface modulation will have to do, it has to be able to compensate for these sort of severe losses, really. Especially if we were to pull this arrangement off in sort of typical indoor distances. We're talking about a few meters, anywhere between 1 to 5, let's say, in the sort of a short distance range. So these attenuation are distance dependent, and we ought to be able to compensate for them on the metasurface side of things. So onto the metasurface element. As a result of these hard to control factors, including attenuation and distance, we are required to be able to do mechanical modulation at a micrometer level, but this has to be phase precise or phase coherent, if you will, because to draw an analogy with established communication systems, it's the phase coherence that will allow us, for instance, in GPS, to detect signals that are buried in noise that is tens of dBs stronger than the signal of interest. So clearly we need to look at this phase coherence modulation at the metasurface size. So we went ahead and iterated over two prototypes really quickly, and these are shown here in this slide. We've got two sort of devices that work in slightly different principles. Clearly, very quickly, a clear winner emerged. We call this device a bimorph device, which is a fancy way of saying that there are 4 piezo actuators that together suspend a plate. These piezo actuators are driven synchronously with a voltage. They then elongate or stretch, if you will, upwards to raise this plate, basically. When you reverse the polarity of the voltage, you have the opposite effect. The geometry of this device was around 10 by 10 centimeter. So the full fabrication details of this are included in our paper. In the interest of time, I'm going to gloss over this for now, and I'll show you a picture of a characterization of this metasurface in our material science lab in Cambridge. We have slowed down quite a bit the frequency by which we're driving this metasurface. In this video, we've got a microscope that is suspended on top of on the side of this plate. This microscope is measuring the elongation of these piezo transducers, and the characterization is done over this microscope screen. So moving on to the third element of this KinPhy channel, we have the reader device. The reader device is basically what it does, it shines millimeter wave energy onto the remote meta surface. This energy is then bounces back. Because we're modulating the meta surface mechanically, the backscattered signals embed this kinetic information, and we go ahead and decode them on the reader side. The reader could be really anything, but it's basically a radar, and there are multiple signaling strategies that one can employ to do that. We just work with one particular one that I'll show later on in the evaluation section. What it then does, there's a demodulation flow. It's a combination of radar signal processing and communication signal processing, the details of which are in the paper. If you're interested, you can ask a question later. I'll do my best to answer them. So moving on to implementation, this slide shows these two main components that make up the KinPhy channel. On the left side, we've got our in-house meta surface. It's basically what I've shown in the video, except that we're using a kitchen foil to enhance the reflectivity of it. The copper plate at the back is mainly for grounding effects, so we really don't use that copper plate for reflection purposes. On the right-hand side, we've got an off-the-shelf radar device from Texas Instruments. It can deliver up to 10 dBm maximum transmit power, and it has data acquisition tools that allow us to grab the raw data. Evaluation was done in our office, really, at Cambridge. For evaluation, in this picture, you can see there is we've mounted everything on a movable platform that we wheeled around. The main evaluation looks at varying two sets of parameters. One set is to do with the physicality of this arrangement. We varied distance between 1 and 5 meters, and we varied the axial alignment of this meta surface with respect to the radar device. And this alignment was varied in yaw and pitch as well, because we're trying to characterize how can we make this standard work irrespective of axial misalignment in a real-world situation. On the other side of things, we varied multiple coding parameters. These included the kinetic coding parameters of the meta surface, but also included things like bandwidth, the utilized bandwidth of the radar reader. So I'm going to just power through the results very quickly. We've got here a detection accuracy metric that is an aggregate metric across all these axial alignments that we've used. You can see basically generally below, between 1 and 3 meters, it sort of was uniformly, the detection was uniformly above 90%, irrespective of axial alignment, and that was mainly due to the coding gain that we've employed on the meta-surface side. This coding gain was able to compensate for distance losses and axial misalignment losses. Another interesting finding was to do with the radar reader. We found out actually, perhaps counterintuitively, that using less bandwidth in fact enhances detection performance. There are all sorts of technical reasons for that. This is all mentioned in, elaborated on in our paper. Moving on to trying to understand how signal strength, or what we call here kinetic signal strength indicator, sort of in similar vein to RSSI, we've got KSSI. So we're trying to understand how the KSSI varied in yaw and pitch and across distances and coding gains. So generally, as you'd expect, the best performance was obtained when the radar was bang on facing the metasurface, and then as you have introduced axial misalignment, you begin to lose signal strength, KSSI. Interestingly though, even when we flip the metasurface altogether to face away from the radar, we were still able to observe decent detection, and that can be understood noting that the actual kinetic energy is coupled through the mass of the metasurface or device really, regardless of actually what orientation it was facing. So that was another interesting finding. The final interesting finding that I'll talk about was to do with non-line of sight detection. What we did is that we thought through our entire data set, we knew where we placed the metasurface, so we had a mask around that range, and we started sort of running brute force detection across the entire data set. It was quite interesting to observe that we're able to do quite a number of successful demodulations from echoes actually that had originated as far as 20 meters away, which is sort of interesting come to think of it, given that we're talking here about micrometer level vibrations. So with that, basically, we've included our sort of feasibility study on this new channel that we call KinPhy, and we think that now we can sort of move forward and try to look at building applications on top of it, because our confidence in it working in uncontrolled situations is kind of there right now. We're of course gated by many other factors, including availability of devices out there. It's early days in the sort of 60 gig world, so we have to wait for sort of solid state transceivers and things like that to become a bit more available. So because this is the last talk, I thought I'll be a bit bullish in imagining how KinPhy can be used in sort of a couple applications that we thought about, just to entertain you guys and sort of wrap up the conference. So the first one, what we thought about, which probably is a bit more on the speculative side, and I'll talk about this a bit more, is beam alignment. Beam alignment is a theme that sort of been looked at in the wireless ATM community quite a bit. Because of the directionality of MillimetreWave, you will need a procedure to set up the alignment of beams in devices that are talking to each other. The way it's done in standards like 11AD, you sort of exhaustively have to sweep all options, one device at a time. One sweeps, the other listens, and then these guys exchange information later on a MAC level to say, okay, this is the sort of combined configuration that gave us the best SNR. Abari and Fania were able to actually come up with, to speed up or expedite this search procedure quite a bit by doing some clever sort of search optimizations there, but it remained a sort of a MAC layer search at its heart, really, although they were able to cut down on the latency of the setup procedure by quite a bit. Now, in KinPhy, imagine how you would be able to do this in the future. Here in this picture, we're showing two nodes. This node 2 here right now has a multi-meta surface arrangement. Basically, we've got a meta surface for each beam direction, and we can encode sort of orthogonal codes for each meta surface and detect those at node 1. So that would basically, in principle, allows us to do beam alignment at the physical layer. without even having to set up a communication link over a traditional millimeter-wave band communication one. Of course, so I say speculative, this is sort of contingent on us being able to design meta surfaces that are fast enough to make this arrangement work with acceptable latency. This is a sort of an ongoing theme of research that we're looking at as well. But food for thought really here. So let's spark this more speculative application and look at something a bit more probably readily sort of relevant. So let's look at security applications in the sort of mobile interaction world. So we picked up a sort of a spontaneous authentication application here, and we're going to sort of talk about how it's currently supported by Apple ecosystem. Let's just say basically you want to mirror your screen, your mobile screen, onto a monitor in an office. Currently it works by you scanning what's available, what monitors, actually you have an Apple TV for that to enable this. You scan for what monitors are available, the monitor displays a PIN key for you to key in, and if you get it all right, you get sort of file casting privileges. Now in KinPhy, we can potentially use KinPhy to implement a two-factor authentication where the first sort of negotiation is done over a traditional communication link that does not even need to be based on millimeter-wave. It could be just traditional sub-6 gigahertz RF. But then the second factor authentication can be done in over KinPhy. Hopefully this procedure is captured in this sort of video that we put together, little animation on this. We've got this external monitor, a person approaches it, they've got their phone on them, a first communication link is sort of queried over RF, normal RF communication one, then the second phase authentication is done over KinPhy. And we think this can be sort of readily enabled with our new channel that we're proposing here. So in summary, basically, am I doing okay for time? Yeah. Okay. Right. So let me sort of summarize where we are here. In this paper, we're proposing KinPhy, a novel mechanical backscatter channel. We think it's particularly interesting because it maps onto an evolution on two fronts that are sort of, we're already moving in that direction. It's an evolution of a commodity tri-band router that has built-in sensing support, not just communication, and this is totally within the realm of possibilities, and as well an evolution of what sort of modern haptics in current devices such as phones. We've shown empirically that it works indoors under realistic conditions and assumptions, and as a low-hanging fruit, we think it affords particular benefit to applications in the sort of area of spontaneous mobile interaction. And I think with that, I'll finish my talk. Thank you very much for listening. Cheers. Sure, yeah. So all the details are in the paper. We've got those. The rate right now is fairly, I should say, slow. It's a bit disappointing, and that's primarily because we're in the early days of fabricating these meta surfaces. So we've got in the codes that I've shown here, for instance, just quickly. We've got here, as you can see in the legend, we have 3 codes that we employ. These are gold codes, spreading sequences, 63, 127, 511. These corresponded to something between 2 seconds all the way to 20 seconds.
So bits per second, what does that mean?
So that actually basically, so if you think about your symbol as this entire duration, the bit per second could be 2 currently, as little as 2 per second, which is a bit disappointing, but we're actually working on a revised meta surface that works in the ultrasonic range, and we mentioned that in the paper, based on piezo films that can be transduced at ultrasonic frequencies. So if we're talking about something that we can drive at 50 kilohertz, we can have this very long code, 511, lasting as little as 2.5 milliseconds. We're sort of in the process of optimizing for that. It's not immediately easy to do so because we want the piezo film as well to be optimized for reflectivity, millimeter-wave reflectivity. And that's is a non-trivial thing to pull off straight away. So we hope in the future we'll be able to.
And the SNR?
And the SNR is, as I show here, okay, I'll wrap it up. The SNR can be, I think this is signal strength 20 dB, let's say 20 dB.
Okay, thank you, Mark, for the chair has something to announce.
Okay, so I think we will start heading down to the buses now, because the buses leave at 6 sharp, and we want to maintain time, as well as this room is getting other things. And just one more piece of information is that there is a section of the museum that is open. It's called the Future City. It's an interactive experience. So people, whichever there are 2 pieces of things, entertainment at the museum today that you can interact with and you can participate in. And the directions, right? You want to just quickly mention directions?
So there are 4 buses right outside of 116th Street and Broadway. We will all walk together right now towards that direction. But if you got lost or whatnot, look for Broadway, 116th Street. And remember, buses are leaving at 6 sharp. And if you miss the buses, go directly to the museum for the City of New York.
All right. So I think you need to get your.
Thank you very much. Sorry. So is this independent? So I think
You'll take this one. Alright, I'll take that with a cable. Sorry. Alright, get the mic, Yeah, well, basically it's 6 to 6. I didn't find any more of these. 4 of these.